Hello, this is the question number 2 from the 2014 exam paper. As with all of these, please do have a go at them first, or at least check to make sure how you would do them before jumping straight to the answers. This is another one that has a little bit of a descriptive part first. So the first part is about the stiffness across the fibres in a continuous unidirectional composite, and it's getting you to explain why the Halpin-Tsai model is better than the Royce model. It's in the notes, I won't go through it in detail. Essentially what you've got here is that the Royce model assumes the stress in the fibres and the stress in the matrix is the same, whereas in fact it actually isn't. And the Halpin-Tsai model is a sort of better measure of getting an approximation to what the stiffness should be, which works much better. Okay, I'll go on to the second part then, which has a unidirectional composite with properties given there. And it says using those values and appropriate equations determine the compliance matrix S. So the first thing we need to do with this is to remind ourselves or look up what the compliance matrix is. It's in the formula sheet at the back of the exam paper. I've copied it here, so it's given by this term here, where the S matrix has these different terms: S11, S12, S22, and S66. Each of those are given by the different terms there. So S11 is 1 over E1, S12 is either Poisson's ratio 1/2 over E1 or the other one, etc. So there's various things we need to work out here. So this is a big deep breath and then just go into the calculations for all the different parts. So if we do that, the first one to work out then is E1, the stiffness along the fibres, sorry. So E1 is just given by the law of mixtures equation, which is VF EF plus 1 minus VF times EM. All of these equations are in the formula sheet, but I'm not copying them because I know them, so I can work them out. VF is 0.55, EF, the fibre stiffness, is 120, 1 minus VF will therefore be 0.45, and the stiffness of the matrix is 3. And if you work that lot out, that comes to be, where's my answer gone? Yeah, it comes to be 67.35 gigapascals. For E2 then, we need to use the Halpin-Tsai model. If we use the Royce model, having in the first part said that the Royce model is no good, then that wouldn't be very sensible and you'd actually lose marks. So in this case, we need to first of all find this value eta, which is given by EF over EM, the stiffness ratio, minus 1 divided by EF over EM plus 1, and that is 120 over 3 minus 1 divided by 120 over 3 plus 1, and that turns out to be 0.9512. Having got that, we then need to use that in the equation for E2. So if we do that, lost my pen, there it is. Okay, if we do that, then E2 is given by EM times 1 plus eta VF over 1 minus eta VF, which is 3 times 1 plus 0.9512 times 0.55 divided by 1 minus 0.9512 times 0.55, and that comes out to equal 9.58 gigapascals. What we then need, the next one that we need is, next simplest one is Poisson's ratio 1/2, because what we can do here to find the term S12, which is just here, we know both E1 and E2, so we could use Poisson's ratio 1/2 or Poisson's ratio 2/1. Actually, Poisson's ratio 1/2 is the easier one to find because it's just another law of mixtures equation. So what we have here is that Poisson's ratio 1/2 is 0.55 times the Poisson's ratio of the matrix, of the fibres, which is 0.24, plus 0.45 volume fraction of the matrix times Poisson's ratio of the matrix, 0.35, and that comes out to be 2895. The final one that we need then is G. Now the thing to remember here is that all the G terms we can assume to be the same regardless of which direction. So we can, again, there's a Halpin psi model for G, which again has an eta value, so we need to work out an eta value, which is shear modulus of the fibres divided by shear modulus of the matrix, minus 1 divided by GF over GM plus 1. In this case, GF is 55, GM is 1, minus 1 divided by 55 divided by 1 plus 1. And that comes out to be 0.9643. And then we have that the shear stiffness is then given by the matrix shear stiffness 1 plus eta VF divided by 1 minus eta VF. And so if we work those out, GM is 1, 1 plus 0.9643 times 0.55 divided by 1 minus 0.9643 times 0.55, and that comes out to be 3.259 gigapascals. So we have all the terms now. We have our terms G, we have our term E1, E2 and Poisson's ratio 1, 2, so we can combine all of those together to give us the S11, S12, S66 and S22 terms. Rather than writing them all out, I've got them here, so that then gives our S matrix as 1 over 67.35, minus 0.289 over 67.35, etc. Now those are a bit cumbersome. A good way of dealing with this is to take out a factor of 1,000, which is often there. So I've done that. I've taken 10 to the minus 3, and then the terms are 14.85, minus 4.29, 0, etc. So that's our S matrix. The units are gigapascals to the minus 1. All of our stiffness terms we've left as gigapascals, so the S matrix, which 1 over the stiffness terms, is gigapascals to the minus 1. Okay, the next bit then is actually using this. So what we have in this case is, it says if the composite in part B is loaded with a tensile stress sigma 1 of 120 megapascals along the fibres and a compressive stress sigma 2 of 60 megapascals across the fibres, calculate the strains in the 1 direction, the 2 direction and the shear strain. And it says you should use the compliance matrix for this. So what we need to do here is to write out what the compliance matrix actually tells us. So the compliance matrix, again, this is in the formula sheet. It relates the strains in the 1 direction, the 2 direction and the shear strain to, so that's our S matrix, not expanded out, to the stresses in the 1 direction, the 2 direction and the shear stress. So in this case we can use that. We've got all the terms, so we can just use that to work things out. So what we can do here is we can say that the strains in the 1 direction, the 2 direction, the shear strain are given by, so the S matrix, we've got our 10 to the minus 3 factor. We've then got the S matrix, which is 14.85 minus 4.29, 0, minus 4.29, 104.4, 0, 0, 0, and 307. So what we then have is that's multiplied by our stresses. In this case we need to put all the stresses in gigapascals because our compliance matrix is in gigapascals to the minus 1. So 120 megapascals is S11, which is 0.12 gigapascals. The stress across is compressive, so it's minus, and it's 60 megapascals, so 0.06 gigapascals, and the shear stress is 0. So what that then means is we can expand that out, and let's have a little bit more room. Oops, not that much. So what that means then is the strain in the 1 direction is 10 to the minus 3 times 14.85 times 0.12 minus 4.29 times minus 0.06 plus 0 times 0. And that comes out to be 2.04 times 10 to the minus 3. We can then do the same for the strain in the two direction. Lost my pen again. Where's it gone? Down there. So the strain in the two direction is 10 to the minus 3 times minus 4.29 times 0.12 plus 104.4 times minus 0.06 plus 0 times 0. And that comes out to be minus 6.78 times 10 to the minus 3. And the final one that we could do then is the shear strain, gamma 1, 2, which is 10 to the minus 3 times 0 times 0.12 plus 0 times minus 0.06 plus 307 times 0, 0. So that's the strains that we've got. A positive tensile strain in the one direction, not surprisingly we're applying a tensile strain that way, and a compressive strain the other way. A compressive strain in the two direction, again not surprisingly because we're applying a compressive stress in that direction and there's a tension opposite it. No shear strain because we're applying the stresses just along the fibres and across the fibres.